In Lab 1, we are instructed to record an object moving at a constant velocity in one direction. I recorded a video of a frisbee rolling across a smooth surface, which is shown here in Tracker. Using the center of the frisbee as the point of reference, the different positions of the frisbee in each frame were measured along the x-axis and plotted on this position versus time graph. The frisbee is moving in the negative x direction at a relatively constant velocity, which can be seen by the relatively constant slope of the graph. Even though the slope seems very constant, it is proven not perfectly constant when the velocities at specific times during the video are compared. The initial velocity, which I found by dividing the difference in positions of the frisbee between the first two frames by the difference in time between the first two frames, is negative 1.2 meters per second, while the final velocity, which I found using the last two frames, is negative 1.3 meters per second. In addition, the average velocity is negative 1.1 meters per second. So even though these differences are pretty small, they still show that the velocity in this video is definitely not constant. This makes sense because in order for the velocity of the frisbee to remain constant, the net force acting on the frisbee must equal 0. Since this frisbee is in the real world and not just a model, it does experience forces such as friction and air resistance. Newton's second law teaches us that force equals mass times acceleration. Thus, if this frisbee experiences force, it also experiences acceleration, and the velocity cannot remain constant. In order to compare our real-life example to an object with a truly constant velocity, a computer model was made. The ball here represents the motion of the frisbee. And here is our code, but we are going to focus on what I consider the most important part of this code, which is the loop where the position and velocity are updated for each change in time, delta t, which is shown here. In order for the velocity shown here to not change, F net, or the net force, was assigned to be 0 right here. The results of this model were put into Excel and graphed on the same plot with the video results. The model's position points are shown in red, while the experiment or the video's points are shown in blue. At first, the points line up rather well, but then the video points start to drift away from the model's line. The positions in the video seem to start changing at a slower pace, or the frisbee starts moving at a velocity of a smaller magnitude. If you recall, the final velocity of the frisbee was measured to be negative 1.3 meters per second. So you might be wondering how this is possible when the frisbee seems to be slowing down on the graph. I think this is the case because if you watch the video again, at the end you can see that the frisbee seems to be moving at a diagonal towards the video camera. And since the frisbee's position was only measured in one dimension, this would make the frisbee look as if it was moving a smaller distance, when in reality the distance was just as long, but just in a slightly different direction. However, once the frisbee has moved far enough on the diagonal, it's closer enough to the video camera to appear bigger and thus make it look like its position is changing more than it actually is, explaining the larger final velocity. So, in conclusion, in order for an object to move at a constant velocity, it must be experiencing a net force of 0, which is explained by Newton's second law stating force equals mass times acceleration. And since forces are occurring all around us in the real world, a truly constant velocity of motion is nearly impossible to find in reality. The end.